All right, well, let's go ahead and get started then. Welcome everybody to the November Science and Engineering Council meeting. We're here on the second Wednesday of the month. So looking forward to today's discussion. Just a couple opening remarks. I'm going to turn it over to Mary to introduce our special guest speaker, and then we'll get into our regular program. So once again, on this time of the year, I just want to remind folks, this is our membership drive to renew memberships and bring in new members. So appreciate that. If please give that some thought, and if you have any questions, reach out to any of the board members here. There's several of us on the phone on the line here today. And thanks again to everybody who donated for the discussion today. Every contribution is super helpful and keeps our administrative expenses supported and other things. So let's see, with that, Mary, I believe you're up, and if you could please help us introduce our special guest before we get into our regular program today.
I'm delighted to be able to tell you that Len Smallboard is with us today. Why am I delighted? Because he is the Chief Programs Officer at the Scholarship Foundation of Santa Barbara. And it is a scholarship foundation that manages the selection of our STEM scholarships. Most of you know that thanks to the generous donation of members, we are able to award scholarships to needy students who are studying in the STEM area. We were able this year, thank you very much, members, to be able to give $2,500 scholarships. So Len is going to talk to us a little bit about the foundation. Welcome, Len.
Thank you, Mary. And once again, it's a pleasure to connect with all of you this early afternoon. Just to kind of provide a quick overview, the Science and Engineering Council and the Scholarship Foundation of Santa Barbara, we've been working together since 1995, awarding students and supporting them as they pursue their post-secondary goals, specifically in the STEM field. So I just want to thank you so much for your participation and support of these students for such a long time. We were going to have one of our students, one of your awardees, join us today, but she is in the middle of a midterm, so which is good. We want her, to take care of her classes and do well academically. So I'll provide a quick biographical update about her, but a little bit just before I start about the student, just about the Scholarship Foundation. We're actually in our 60th year of existence. So we started in 1962 with $900 worth of awards. And then last year we awarded just over $7.7 million to Santa Barbara County students, more than 2,100 Santa Barbara County students. And in the last 60 years, we've awarded more than $140 million to 60,000 local students. 99% of the dollars stay local and support students from Santa Barbara County. So we're just really just glad that we could support our students here locally. As Santa Barbara County high school graduates, all of them are eligible for 5 years of undergraduate support, but also an additional 4 years of graduate school. So that could be an MBA, a PhD program, law school, or medical school. So every year we'd have to turn away eligible students, but thanks to organizations like yours, we're able to award more and more students each year. So thank you so much for your financial support and contribution for these students. The student I'm going to highlight today is actually, her name is Guadalupe Rodriguez Bautista. She's currently in her third undergraduate year at UC Irvine, and she is majoring in engineering, but she's also volunteer on campus with various women's groups, but also with Pantry on campus to help supporting students who are in need. Her goal after graduating from UC Irvine is to either pursue her graduate degree in engineering or attend law school. So she's been with us now going into her third year, and she just she sends her gratitude and just deep appreciation for your support, and she wishes she could have been here, but once again, midterms took priority today. So once again, I just want to thank you for your support. Guadalupe is doing great, and we're looking forward to her renewing her application for the 23-24 academic year, which will be her last year at UC Irvine. And then, as I mentioned, she's also going to be eligible for some graduate support as well. So that's an update on Guadalupe. If you have any questions about the Scholarship Foundation, I'm happy to answer some really quick if that's okay. But other than that, I just want to thank all of you once again for your partnership and support of these students.
Thank you.
Well, thank you all, and if any follow-up questions, Yvonne and Mary both have my contact information, and I'm more than happy to answer any follow-up questions via email. Thank you.
Great. Thank you.
Yeah, thank you.
So let us introduce Yvonne DeGras, our program chair, who will introduce our speaker today and tell us about upcoming programs.
Great. Thanks, Mary. Hello, everyone. Our next meeting will be on December 14th, and we'll be sending out an email soon with information about the topic and speaker for that meeting. Just wanted to mention that subtitles are available during today's talk if you enable live transcript in your Zoom window. And you can type questions into the Zoom chat during the talk today or ask them after the talk. Today, we are happy to have Dr. Alex Moreland speaking to us. Dr. Moreland is a postdoctoral scholar at UCSB in the BASIS Group Research Group, which is the Center for Polymers and Organic Solids. He's also co-founder and CSO of Zeresta, I think I'm pronouncing that correctly, a local startup company for the last 4 years. His research is centered on developing a novel class of antibiotics to combat the antimicrobial resistance crisis. Dr. Moreland moved from his hometown of Morro Bay to Santa Barbara in 2008, completed his bachelor's at UCSB with majors in biology and chemistry in 2012, and moved across the street to work at Raytheon Vision Systems in Goleta. Then he returned to UCSB in 2014 to pursue a PhD in chemistry. He's speaking to us today on paradigm-changing antibiotics to combat the antimicrobial resistance crisis. So, Dr. Moreland, take it away.
Thank you for the intro, Yvonne, and thank you to the Science and Engineering Council for the opportunity to present some of the work that we're doing in Guy Bazan's group. So, as you saw, the title is Paradigm Changing Antibiotics to Combat the Antimicrobial Resistance Crisis. I'm going to start out by explaining what the AMR crisis is. I just want to say that this is going to be 15 minutes, which is definitely not sufficient to really dive deep into this topic. But what I hope you come away with is a feeling that I share that this is a global health threat that deserves more attention than it's getting. And then the majority of the talk will be about our technology that we've developed at UCSB, which focuses on a class of compounds called conjugated oligoelectrolytes, COEs. And I'll discuss our collaborative network, the inception of the tech, and then a couple advancements we've made recently. And then I'll end with kind of the state of the art of this technology. And for the second part, I hope to convince all of you that COEs could be paradigm changing in this fight against the AMR crisis. All right, so as I mentioned, I work for Professor Guy Bazan. He used to be at UCSB. He recently moved to Singapore, so he's now at NUS. At UCSB, we have a long history of working through this department called the Institute for Collaborative Biotechnologies. that's where the tech was born, essentially. And more recently, as we've shifted to antibiotic development, this work through the ICB is in partnership with Walter Reed Army Institute of Research. More recently, we have funding from Cystic Fibrosis Foundation, which is through the Department of Chemistry and Biochemistry at UCSB, and CPOS, which is the Center for Polymers and Organic Solids. This funding from the CF Foundation supports my fellowship, as well as another research grant that is in collaboration with National Jewish Health. And then in the so-called Bazan Lab East in Singapore, Guy is at NUS, but we also have collaborators at NTU, which is another major university there, CELSI, which is something of a national lab. And a lot of this work is contracted through Evotech, which is a contract research organization that has a long history in antibiotic development. And then Zaretza is a spin-out company from UCSB, and it's licensing IP related to this technology from both UCSB and NUS. This is somewhat of an acknowledgement slide. I just want to say thanks to a few technical people who contributed to the data that I'll show. So of course, Professor Bazan, and then also at UCSB, we have Dr. Jacqueline Limwongyut, and he, similar to me, was a grad student in the group, and he defended earlier this year, and he's now a postdoc with us. And then in Singapore, we have Dr. Jamie Hinks and Dr. Kai-Shi Zhang, some former group members. And so some of these technical folks are part of Zaretza, and also at Zaretza, we have kind of our BizOp group, which include Patrick Dietz and Robert Podstrozny and Dennis Houghton. All right, so the first part is about the AMR crisis, and why I think everyone should believe that this is a global health threat. Before we talk specifically about what the crisis looks like, I don't think I necessarily need to remind people at this point that an infectious disease threat somewhere in the world is a threat for all of us. AMR currently is most acute in low and middle income countries, but that doesn't mean we should wait until it's really severe everywhere in the world. Just a quick definition of antimicrobial resistance. Essentially, bacteria, when exposed to the selective pressure of an antibiotic, evolve to become less sensitive to that antibiotic, and sensitivity eventually becomes so low that it's infeasible to treat a patient with enough of the antibiotic to kill bacteria that are infecting that patient. And we're talking about this in 2022, but it's important to note that we've known about this evolutionary process longer than we've even had antibiotics. So Alexander Fleming, in his Nobel lecture in 1945, made a point to describe the potential for this crisis. And he said, by exposing microbes to non-lethal quantities of the drug, we can make them resistant. So to describe the crisis, I think we can start out by looking at where it might go in the future. So there's a report from 2016 by the economist Lord Jim O'Neill. And in this report, he estimates that AMR will cause 10 million deaths annually by 2050, and it will result in a loss of $100 trillion in global GDP. So to put the 10 million deaths in context, that means that AMR would be a bigger killer than cancer and diabetes combined. There are some other estimates. So the CDC published a report about the AMR threat specific to the US. And in this, they said that around 36,000 deaths occur in the US annually as a result of AMR. And then more recently, there was a publication in The Lancet that puts the global estimate at 1.27 million attributable deaths to AMR per year. And just doing the math, that means that even during the short course of this talk, there will be 145 deaths related to AMR. Now, 1.27 million deaths is very significant, in my opinion, but maybe more significant than that is the fact that modern medicine is dependent on the availability of effective antibiotics. So one way we can think of antibiotics as the cornerstone of modern medicine, and that's because a lot of the advancements we've made in medicine since the development of antibiotics rely on the availability of a way to treat infections that are likely to arise as a result of these other interventions. So, many treatments for autoimmune disease or cancer therapy weaken a patient's immune system, and then obviously things like surgery provide a route for bacteria to infect the patient, and so we need to have antibiotics to treat those infections that are certain to arise in patients. And for this reason, continued development of new antibiotics is paramount to the progression of modern medicine. But what we've seen is the opposite, actually. So as AMR has been progressing, the approvals of new antibiotics have been decreasing from the 80s to the present day. So on the left, you can see new approvals are going down pretty markedly. And maybe more concerning is that over the last couple of decades, a lot of big pharma has exited this space. So on the right, this is a German news outlet has this article or video, and you can get it in English. It's really a very good description of the AMR crisis. But this one screenshot shows the year in which all of these big pharma companies either divested or abandoned their antibiotics programs. So there are, of course, huge technical issues in developing antibiotics. A lot of the low-hanging fruit has already been picked, so it's increasingly difficult to find new antibiotics, and the market is also problematic. Fortunately, lawmakers in the US and in other countries have taken note of this issue, and they recognize the AMR crisis for what it is. And so I'm hopeful that in the next few years, they'll be true to their word and provide new incentives to reinvigorate the antibiotics pipeline. All right, so the rest of the talk will be about what we're doing in the Bazan lab and at Zaretsa to try to develop our tech into new life-saving therapies to combat the AMR crisis. And I just want to say that this talk is from the perspective of me as a UCSB researcher and not so much on the commercial side of things. So our technology is based on this class of chemicals called conjugated oligoelectrolytes, or COEs. Three characteristics are important for the definition of a COE. So one, they have a rigid hydrophobic core. Two, they have charged hydrophilic ends. And then three, they have a specific length dimension. And in this case, length means from a hydrophilic group on one side of the molecule to a hydrophilic group on the other side of the molecule. So we have a general cartoon as well as one example that the group made in around 2010, and it's been well studied. So these three structural features provide a very important property for the function of COEs in terms of antibiotics as well as other applications for these molecules. And that is that when you add them to living cells, they spontaneously intercalate across the membrane of the cell. And we've shown in a number of different ways that this interaction with the membrane looks like what is shown on the top right, where the COE is really spanning the membrane. And this property is important for many applications of COEs, but it's a vital feature of their mechanism of action with respect to antimicrobial properties. But it's important to note that this membrane active mechanism is distinct from other membrane active antibiotics. So I've mentioned now that there are other applications that COEs are used in, and in fact, the original application was very different from antibiotics. So originally, COEs were developed for use in these devices called microbial fuel cells, which is shown in the left box there. And essentially what this device is it's using metabolism of bacteria to produce power. And so you can harvest electrons essentially directly from the bacteria to create current. And the purpose of the COEs in these devices is to facilitate that extraction of electrons from the bacteria. So there was a paper in 2013. We probably worked on this from 2010 until well into my time in the group starting in 2014. And as I mentioned, this was work through the ICB at UCSB. And at the time, this was a collaboration with Army Research Lab. And so at the bottom picture there on the left, I was fortunate enough to work for a couple weeks in their lab in Silver Spring on a couple different occasions during my PhD. And this mural that's shown here is in their lobby. And the brightly colored green and blue cartoon on the right of that mural is actually a depiction of our COE technology inside of a membrane. So it's nice to know that they felt strongly enough about this collaboration and liked the tech enough that it's something that every visitor of ARL sees. So when I joined the group in 2014, that was the primary application of COEs. My thesis eventually became sort of the diversification of COE applications. I'm not going to talk specifically about what those applications are, but on the right is a depiction of COEs that I think is useful for understanding how we're able to tune structures. And so I like to think of COEs as an assemblage of colored blocks that follow a discrete pattern. So yellow block, green, blue, red, blue, green, yellow. And so every COE will follow this pattern, but the nature of each block can be changed. So by rationally selecting different blocks, we can change the chemical properties of the COE, thereby impacting the COE's effects in a cell. During the course of the work with microbial fuel cells, as well as these other applications, we found that certain COEs didn't work in their intended application. And we attributed that to their toxicity to the bacteria. So for most of these applications, we need the bacteria to be alive. So we were assuming that some of the COEs were just toxic to the bacteria and therefore didn't perform well in the intended application. In 2016, some researchers from our group decided to explicitly check that. And so they tested the activity of a number of COEs and found two things. One, they confirmed that those COEs that were not working in the other applications were killing the bacteria. And two, they found that there was multiple obvious trends relating the chemical structure of the COE to its ability to kill bacteria. And so somewhere around 2008, the group pivoted to developing COEs as antibiotics. So before I talk about any data, I just want to explain kind of the most fundamental assay in antibiotic development. And this is the minimum inhibitory concentration, which is essentially the way that we measure how active a compound is. So it's a really simple assay, usually done on 96 well plate format. You make a serial dilution of the compound that you're testing, and then you add a small amount of bacteria. You incubate the plate to allow the bacteria to grow, and then you measure the optical density at 600 nanometers to quantify how much the bacteria grew. So the more they grow, the more turbid the solution will become, the higher the optical density. And then the MIC is defined as the first point where bacteria growth is limited to 10% of the control. So on the plot on the bottom left, you can see the lowest 3 concentrations have a high optical density, meaning the bacteria were able to grow. And then that 4th point, you can see the optical density is very low, indicating that at that concentration, the bacteria were not able to grow. So back to the paper from 2016, the trend that was observed in chemical structure is essentially that the shorter the COE, the more active it is. So on the top right, we have this cartoon description of this trend where you can see the longest COE has the highest MIC, meaning it is the least active. As we make the COE shorter and shorter, the activity gets greater until we get to this COE that's called COE2 here. And this COE breaks the trend. So it got shorter, but the activity didn't get higher, it actually got lower. And in the paper, this was attributed to an observation that this COE did not have a strong affinity for bacteria, whereas all of the longer COEs did have a strong affinity. And so our first optimization effort was to increase the hydrophobicity of this molecule. In so doing, we're hoping to improve the affinity for bacteria because we assumed that COE2 was just too water soluble to, there wasn't any driving force to move from water to the membrane of the bacteria. So we developed this new derivative, COE2 hexyl, with increased hydrophobic content shown in green. And it's important to note that the length of the COE, that is the distance between the charged groups, didn't change. So this is still a short COE. However, it's more hydrophobic, which increased the affinity for bacteria. And we did recover the trend with increased activity. So this molecule is a good starting point for our development. We found that it's active against every bacteria that we've tested so far. However, it's somewhat detergent-like, which doesn't make for a good antibiotic. When you go to the pharmacist and get a prescription for antibiotics, they don't give you a bottle of soap. In general, soap is somewhat indiscriminate in killing cells. And so this leads to, this detergent-like property leads to high cytotoxicity, meaning that this compound is also toxic to mammalian cells. At roughly the same time as we were developing COE2 hexyl, I was working on a separate project. The beginning of this project was not related in any way to the antibiotics, but it's a good explanation for this Lego principle. And it also gave us a very important insight that did relate to antibiotics. So in this table of COEs, you can see on the top row, those COEs have 5 rings in the core, and then 4 rings, 3 rings. The bottom row has 2 rings. So we were just changing the block related to the core of the COE. And then across these blue diagonals, the length of the chain in each COE is different. So in the first diagonal, the length of the chain contains 4 carbons, then 6 carbons, 8 carbons, 10 carbons in the the furthest right diagonal. And when we order the COEs in this manner, you can see that the total length in COEs within the same column is similar. So on the left, those two COEs have a total length of approximately 3 nanometers. And then all the way on the right, those COEs have a total length of approximately 4.5 nanometers. So the reason I was making these COEs in the first place was to try to find a structure that would be not toxic to bacteria, but would permeabilize the cell. So essentially, I was trying to find a detergent-like molecule that was not active. And so this obviously relates to the antibiotic effort. In that effort, we want the exact opposite. We want something that kills bacteria, but is not detergent-like. And so ideally, what we would find is that the structural features of the COE that determine activity and surfactant-like behavior are different. And in fact, that is what we saw. So in this table, the green box is highlighting the MIC. So this is the activity of the COEs against E. coli in this case. And the R and P, or the correlation and significant values here, tell us that activity is predominantly related to the total length of the COE. In the red box, we have two different assays for membrane permeability, which is a descriptor for the surfactant-like behavior. And in this case, what we find is that we have good correlation and significance with either the core length or the pendant length, that is the chains on the COE. So what we can gather from this is that a shorter total length will give us higher activity. Having more aromatic rings and shorter chains will give us less permeability. And so with this, we can begin to think about structures where we can increase the activity and reduce the surfactant-like character of the molecule. So to do this, we develop another set of COEs. In this case, as shown on the left, all of these COEs have 3 aromatic rings in the core. And now the variables that we're changing in the structure are these 2 different chains. So the length of the chain between the oxygen atom and the nitrogen atom is denoted N, and the length of the chain beyond the nitrogen atom is denoted M. And so we made a series of molecules varying N and M. In this first table that's in red, this is the activity of these different COE derivatives. And so what we can see is that towards the bottom and also somewhat towards the right of this table, we have lower and lower MICs, meaning higher and higher activity. In the second table, this is an analogous assay to MIC, but with mammalian cells. So in this case, we want the number to be as high as possible because that indicates that the COE is not toxic to mammalian cells. And then in the final table on the right, this is sort of a selectivity index, which is simply just the IC50 divided by the MIC. So this gives us a sense of how selective the COEs are for bacteria cells versus mammalian cells. And what you should note here is that we have this sweet spot sort of where we have a very high selectivity. So these compounds have good activity against bacteria and they're non-toxic mammalian cells. And I just want to point out that the selectivity of that first antibiotic derivative, COE2 hexyl, was only about 4. So that means through our first series of derivatizations, we improved the selectivity at least an order of magnitude, if not closer to 2 orders of magnitude. So those are the only specific sets of molecules that I'll talk about, but I will say that we've gone through this iterative process multiple times now. We've created at least 150 derivatives at this point, and the derivative that I'll talk about most for the rest of this talk is COE1B. And I just want to make the analogy of these iterative designs essentially equating to trying to balance a series of teeter-totters that are connected by springs. And so, we may increase activity a lot in one derivative, but that's going to have that same structural change in the COE is going to have impacts on all the other properties that are important for the development of antibiotics. And so this process is essentially trying to maximize the good properties of the COE and minimize the undesirable properties. At this point, I also want to note that there's a nomenclature change of sorts. So there's a long history for COEs. So to differentiate, these COEs that are intentionally designed as antibiotics from previous groups of COEs, we call these this subset of COEs anti-infective conjugated electrolytes. So COE1B is equivalent to ACE1B. Through the course of these iterations in chemical structure, we also refined the scope of our targets for these antibiotics that we're developing. So we essentially have two main focuses now. One is lung disease caused by non-tuberculous mycobacteria, or NTM. As the name suggests, this is a relative of the bacteria that causes tuberculosis. And similar to tuberculosis, NTM causes chronic, debilitating respiratory infections. NTM is ubiquitous in the environment. It's really everywhere. It's in lakes, in water systems. It's very tolerant of heat, so you often find it in shower heads. But for most people, it doesn't cause infection. However, for people with underlying risks, such as cystic fibrosis, COPD, or those that are immunocompromised or elderly, this can cause severe infection. So that this bacteria is not necessarily what we would consider AMR in the traditional sense. It didn't evolve through exposure to antibiotics to become resistant. It's just that this bacteria has always been intrinsically resistant to antibiotics. So even before we had antibiotics, this bacteria already had mechanisms to evade those treatments. And in fact, there's never been an effective therapy for this disease. So of course, as I mentioned, people with CF are at risk for this. So the Cystic Fibrosis Foundation is interested in this, and our funding for this project is coming from CFF. The other area of interest for us on the right is what you would consider the traditional AMR. And so the specific bacteria that we're interested in are guided by what the WHO and CDC consider the greatest threats. So that includes Pseudomonas aeruginosa, Enterobacteriaceae, which is a family of bacteria that includes E. coli, as well as a number of other common human pathogens, and Staph aureus, specifically methicillin-resistant Staph aureus. So this is MRSA, or sometimes just called MRSA. And the reason the WHO and the CDC consider these important threats that we need new treatments for is because they do cause a lot of cases in people. There are few good treatment options for them, and the pipeline of new antibiotics is sparse for these bacteria. So this is the focus of my fellowship from CFF, and this is also an area that we're collaborating with Walter Reed. So these bacteria can cause respiratory infections, which is why CFF is interested, but they're also very common in wound infections, such as those you would see in a traumatic wound of a warfighter. All right, so we'll start with the data with this state-of-the-art ACE1B. This is data from our collaborators at Walter Reed, and essentially what they've done is they've measured MIC against 100 different isolates of Pseudomonas. And so instead of getting the activity against one specific strain of Pseudomonas, this is kind of a population-wide description of how active compound is against a particular species. So what the data are showing are the number of those 100 strains for which they have an MIC of the value on the x-axis. The first observation to make is the ACE1B has a comparable activity to the commercial antibiotic levofloxacin, which is our control in this case, which is obviously an important feature. You know, we want our antibiotics to be at least as active as antibiotics that we know already work. Another more subtle feature that you can notice is that the shape of the curve for the bacteria treated with ACE1B is a lot sharper, a lot narrower than that with levofloxacin. And so to look at this in more detail, we can stratify these 100 strains by how resistant they are to antibiotics. So the data on the right are the same MICs for the same bacteria, except now the bacteria are grouped according to their resistance phenotype. So susceptible means they're not resistant to anything. Non-multi-drug resistant means they're resistant to one antibiotic. Multi-drug resistant means they're resistant to two. Extensively drug resistant means they're resistant to more than 2 classes of antibiotics. And pan-drug resistant means they're resistant to all known antibiotics. And so what we see here for levofloxacin is that as the bacteria become generally more resistant to more classes of antibiotics, the specific resistance to levofloxacin becomes more acute. So the median value within each of these groups continues upward. However, for ACE1B, we see that the median value for these different groups of Pseudomonas stays at 8. And even the pan-resistant strain, the one isolate of Pseudomonas, which is resistant to all known classes of antibiotics, has the same susceptibility to ACE1B. And so this is important because it means that ACEs are not susceptible to the same resistance mechanisms that make other antibiotics not effective. So that's pre-existing resistance. Another part of this story is resistance evolved specifically towards new compounds. So in this assay, PA01 is a particular strain of Pseudomonas. And what we've done here is over the course of 3 weeks, we continually increase the concentration of ACE1B, or these 2 commercial antibiotics, tobramycin and ciprofloxacin, and try to promote the evolution of resistance in this Pseudomonas. And what we find is that through 3 weeks, we can develop a little bit of resistance to ACE1B. So at the end of 3 weeks, the MIC is 4 times higher than it was at the beginning. However, compared to the commercial antibiotics, this is very low. So for ciprofloxacin, at the end of 3 weeks, the MIC is now 32 times higher. And for tobramycin, it's 64, 128 times higher. So what this means is that not only are ACEs not susceptible to pre-existing resistance, but it's very difficult for bacteria to become newly resistant to ACEs. So here's another study with PA01. In this case, these are not planktonic bacteria. These are bacteria that are in a biofilm. And biofilms, although not necessarily directly correlated to AMR, they are important in the clinic. And that's because even if the bacteria within the biofilm should be susceptible to a particular antibiotic, the formation of the biofilm prevents those antibiotics from working. So a biofilm is essentially a matrix that the bacteria excrete that includes a variety of biomolecules. And you can think of it as something of a shield for the bacteria. And in fact, most antibiotics have no impact on bacteria that live in a biofilm. And so this is important in the clinic because this is a common cause of recalcitrant infections. So you might have a UTI, you take an antibiotic, UTI seems to clear up, but then a week later, you have the infection again. And that's because the antibiotic that you took killed all the free living bacteria, but didn't kill bacteria that are within a biofilm. So the way this assay works is we're using a luminescence kit that essentially correlates to the number of living bacteria. So if we have a 1 log reduction in luminescence in this assay, it correlates to a 1 log reduction in the number of living bacteria. And what you can see is with tobramycin and ciprofloxacin, even at huge concentrations, this is, at least 100 times higher than what you'd be able to deliver in a person. There's really no impact on the bacteria living in the biofilm. Polymyxin B is essentially our positive control here. So polymyxin B is one of the key active ingredients in polysporin, and it's known to be one of the few things that is highly active against biofilms. And what we see for ACE1B is that it's maybe not quite as good as polymyxin B. However, it's significantly better than the other antibiotics. So we need about 4 times more ACE1B to approach complete eradication compared to polymyxin B. However, this is still good news for the development of ACEs because it shows that this derivative is already quite active against biofilms, and we do likely have the ability to improve the biofilm activity. So all of the data to this point have been in vitro, and I'm sure some people are starting to wonder how well these things work in vivo. And so we have a study here in mice. The timeline across the top is basically the full course of this experiment. So on days -4 and days -1, we give the mice cyclophosphamide, which essentially knocks down the immune system of the mice. And the reason we need to do that is twofold. First, mice have a very good immune system, and it's hard for them to catch bacterial infections. So we need to reduce the immune system so that we can establish an infection. And then the other related point is that by knocking out the immune system, we know that any effects we see in this experiment are directly related to the treatment and not necessarily impacted by the immune system of the mice. So then we infect the mice. Sometime later, we treat the mice. In this case, it's 1 hour, but depending on the model, this can be longer if you want the infection to establish for a longer period of time. And then in this case, 24 hours later, sacrifice the mice, homogenize the tissue, and then from that tissue homogenate, we can count the bacteria to determine how many bacteria are in that organ. In this case, this is a lung infection model. And so the organ in this case that we're looking at here is the lung. What we see is that for the positive control colistin, we get about 2 log reduction in the number of Pseudomonas that are in the lung of these mice. And we also see that this ACE derivative has approximately the same impact, meaning it's just as good at clearing the infection as our positive control. On the right, we have essentially the same experiment. There's no positive control in this case, but we know that the positive control should give us a 2 log reduction in bacteria. And what we see, again, we have the same ACE derivative with its 2 log reduction, and ACE1B here, we also get a 2 log reduction at a lower concentration even. So this ACE derivative at 5 milligrams per kilogram gives us approximately the same effect as our positive control colistin does at 10 milligrams per kilogram. So we've done a similar assay with other bacteria, including Klebsiella pneumonia, MRSA, and with our collaborators at Walter Reed, we're looking at Pseudomonas wound infections, and in all of these cases, we do see a good response, similar to the two shown here. It's important to note that in these lung infection models, the comparator antibiotics as well as the ACEs were delivered intratracheally, and this is used as a model for inhaled antibiotics. So this is of importance to people with CF, because in that population, the use of inhaled antibiotics is prevalent. However, in the general population, there aren't actually any approved antibiotics for inhaled delivery. So, this data is very important for our work with Cystic Fibrosis Foundation, but in the larger context of AMR, we would like to have ACEs that are effective in these animal models with systemic delivery, so oral or intramuscular or intravenous. So unfortunately for this ACE1B derivative, while it has great activity and it's very selective for bacteria over mammalian cells, and we've shown good efficacy in mouse models when delivering it intratracheally, the systemic tolerability in mice isn't high enough. So essentially it's too toxic if it's given intravenously. So it's tolerated by mice if you give it directly to the site of infection, but if you try to deliver this to the blood, it becomes toxic to the mice. So the most recent optimization that we've done, this was sometime in the summer of this year, was targeted specifically at improving the systemic tolerability. So we made a number of derivatives, and one key derivative from that new optimization effort is ACE1BCF on the right. And what we found is we did lose a little bit of activity. So it was 2 to 4x less active than ACE1B. However, we had a huge increase in the tolerability in mice, something like 100x, meaning we can give 100 times more of this compound to a mouse without having it be toxic. And so this is kind of the teeter-totter analogy where we've slightly impaired one of the desirable properties, but we've vastly improved one of the other desirable properties. And so the ratio between these two effects is can be assessed as a greater than 10x improvement. So this is getting close to the end here. This is now more mouse model infections. However, these are with MRSA, and in this case, the comparator and the ACE were delivered intravenously. And so on the right, we have a thigh infection model. And what we see is that the ACE derivative, while not as good as vancomycin at these concentrations, does result in a 1 log reduction of bacteria from about 10 to the 7th per thigh to about 10 to the 6th per thigh. And this 1 log reduction is very important because this model, as well as the lung infection model on the right, are very well established and very well correlated to clinical success. And so what I mean by that is it has been shown that if you can achieve 1 log reduction in this thigh infection model, that is predictive of being able to treat a human patient. And so you can see ACE1BCF just barely squeaks below that 1 log reduction, green dashed line. On the lung infection on the right, again, like I said, this is well established, and it's been shown that if you achieve net stasis meaning your treatment group doesn't show any growth relative to the before treatment. So what you can see here is before treatment is a little bit below 10 to the 6th, and then the untreated, that is 24 hours later, the bacteria in the lung have grown up. So now there's an order of magnitude more bacteria. So if you can prevent that growth, that's predictive of success in community-acquired pneumonia. And if you can show 1 log reduction in bacteria, that's predictive of hospital-acquired pneumonia. So you can see in this case, neither the comparator nor the ACE reach that 1 log reduction, but we do see that the ACE at least achieves stasis in this case, showing that it does have promise for community-acquired pneumonia. One important related note here is that we don't know how rapidly this ACE is cleared from the body. And so we're giving a single IV injection, and it is possible that by giving this as a single injection, it goes from the blood, quickly moves to the lung, but then might also be quickly removed from the lung and excreted by the mouse. And so it's possible that something like repeat dosing, not change the structure at all, but just change the way that we're dosing the mice might actually improve the outcome further. All right, so I hope from that I've demonstrated to you that this framework has a tractable structure activity relationship that we're able to use to tune the properties in such a way that we improve the characteristics of the compounds. The platform has a high selectivity for bacteria over mammalian cells with comparable activity to approved drugs, no pre-existing resistance, and a low propensity for the development of new resistance, plus activity against bacteria within biofilms, which is not typically something that you see with antibiotics. And now with our recent studies have shown that this framework is effective in vivo. So what we're working on now, and kind of the next iteration for us, is to try to get another order of magnitude improvement, this time in therapeutic index. And essentially therapeutic index is the ratio of the lowest effective dose to the maximum safe dose. And so this is something of the holy grail metric for drug development in general. You really want to make this as wide as possible, such that maybe you have an order of magnitude difference between an effective dose and something that would be toxic to the patient. So currently, this last ACE derivative that I talked about, the therapeutic index is probably somewhere around 1 to 3. There are approved drugs that have low therapeutic index, like 3. However, we think that reaching 10 is a reasonable target, since we have shown the ability to tune the structures and get these order of magnitude improvements in key parameters. And of course, this is now, it shows good progress towards our ultimate goal of developing ACEs into life-saving antibiotics to combat the growing AMR global health threat, as well as other difficult to treat infections like NTM in cystic fibrosis patients. And with that, I'll thank you all for your attention, and I'll take any questions that you might have.
Great, thank you so much. I just wanted to go through some of the questions in the chat first. And this was also a question I was wondering about. George asked, what mechanism does the ACE kill the bacteria? What's the action method?
So we have a really big study with Evotech right now, specifically to determine that. So we do know a couple things that it's not, to start with. So they're not destroying the membrane per se. So if you treat bacteria and kill them and look at them under a microscope, they still look intact. If you treat bacteria with soap, some detergent, what you'll see is that the whole cells just explode. Mm-hmm. We also know that the effects on the cell are not the same as we would see with other membrane active compounds. So colistin, the comparator antibiotic in a couple of those studies, is membrane active. However, when we look at the specifics of what happened to cells treated with colistin or ACEs, they're different. And that goes for other membrane active compounds, such as daptomycin or gramicidin. So our best guess, I would say, at this point, is that that process of intercalating into the membrane disrupts the bulk properties of the membrane. And there are key essential proteins in bacteria that require a very specific membrane region around them. And so we think the ACEs disrupt those key regions around membrane proteins, and that causes those membrane proteins to not function, and that causes the bacteria to die.
Okay. Mary, did you have a question? You were.
I asked a question at the very beginning.
Okay.
And it's basically been answered
Yeah.
about choosing bacteria over the human cells, but those studies have been done.
Yeah, but that
I think
so
George's
that
other-
kind of leads into George's other question about the
Exactly.
pathogens, the bad bacteria we don't want versus the beneficial bacteria.
Yeah. So if you test it in vitro, my assumption is that the compounds would be equally active against pathogens and commensal bacteria that you do want. However, it seems like ACEs are cleared from the body through the renal pathway. And that goes for IV injected as well as inhaled ACEs. So inhaled ACEs eventually get to the blood. IV injected ones obviously start out in the blood, and then they're cleared by the kidneys. And so if clearance is predominantly through the kidneys, commensal bacteria are in the GI. So if you're not ever exposing those bacteria to the compound, then you're not going to have any problems with, killing the bacteria that you don't want to kill.
Another question is, you mentioned the inhalation and injection. Have you done topical studies like on wounds?
Yeah, so the wound models that we're doing with Walter Reed are topical. A big part of drug development in general, but maybe even more so in topical drugs, is the formulation. And so we haven't started exploring different formulations. So currently we're just dissolving our compounds in saline and adding that directly to the wound. And with that, we do see good effects, but it's possible that improving the formulation could compound those good effects.
Do other people have questions? Go ahead and unmute yourself, or raise your Zoom hand or something like that.
This is George. I have one more question. What about bacteria developing resistance to the ACEs?
Sure. So, sorry, I'm just going to slowly move backwards here. So there's a number of ways to assess that the chance of that happening. The easiest way is this in vitro assay that we did. There are obviously more complicated in vitro ways to assess this. And then of course you can also do this in mouse models, treat the mice and see if the bacteria at the end have become resistant or not. However, most of those more complicated models still show good correlation with this very simple model. So a more descriptive way to explain what we're doing here is essentially every day we're measuring MIC. So we're doing that MIC experiment, and then the highest concentration that was tolerated by the bacteria, meaning the highest exposure that still allow the bacteria to grow, we use that as the inocula for the next day. And so we're continually, trying to make these bacteria develop some form of resistance. And the result of, 3 weeks only leading to a 4x increase in MIC is very good compared to, these two antibiotics as well as other classes of antibiotics. One other key way to assess this resistance is essentially taking many bacteria, like 10 to the 9 bacteria, some huge number like that, expose them to the compound, and then plate those on solid media. And so you'll get colonies for every bacteria that was resistant or, had some genetic mutation that made it resistant. And in that kind of assay, we also see that the ACEs outperform other classes of antibiotics, in some cases by an order of magnitude, and in some cases by 3 or 4 orders of magnitude, meaning that there's a significantly lower probability of a bacteria evolving some kind of resistance.
Thank you.
This is Mary, isn't that in part because interculation is really a reversible process as opposed to the binding that happens with the antibiotics?
Yeah, exactly. So a lot of resistance, first of all, the membrane being the target is good in the context of resistance, because all of those other antibiotics need to get to intracellular targets. And so the bacteria have good ways of preventing those compounds from going in, or in some cases excreting those compounds once they do get in. And then, as you said, there's some reversible interaction between those antibiotics and their specific target, whereas this interaction, we haven't proven that it's irreversible, but
No.
I think that it is close to irreversible.
I thought interculation is itself a reversible. The very act of intercalating, one can go in and then back out, in and out, in and out.
Yeah, so I think in this case, it can go in and out. It's just that, if this is an equilibrium, there's a very high, driving force towards the inside the membrane state,
yes,
as opposed to the outside of the membrane state.
But the compound itself stays as the compound itself, and it isn't bound, so it's not used up in the same way, is what I'm trying to say.
Yeah.
I was wondering, you said that it's excreted renally. Would that end up, how stable is the compound? Is it, would it still be active, in septic systems?
Yeah, probably.
Okay.
So that it's actually common for a number of antibiotics, and of course that is a way that you can develop resistance. You don't have to develop resistance in a patient. You can develop resistance in bacteria somewhere else. However, the factor of dilution is hopefully immense. Once you dilute it into septic system or something like that. But the stability is high, so most of the drug that you put in is unchanged by the time it comes out.
Do other people have questions? I thought you might talk about Zeresta and sort of what your future plans are. You mentioned working on the therapeutic index. If you've boosted that, then what's next?
Yeah, so currently, from that first slide, the way that this is organized at this point is essentially all of the advancement of the tech is being conducted at academic institutes, so UCSB, NUS, etc. And then Zeresta is essentially just holding the IP. Ideally, the next step for Zeresta would be to move into its own space. Something like the incubator at UCSB would be great. But at the same time, we're going to continue to leverage these other these other sources of new information related to the framework. I think currently NTM lung disease is more of a focus of Zaretza, at least on the commercial side of things. That has to do with how well the ACEs are performing relative to current treatments. So in that case, the ACEs are looking better than current treatments, and also the market is a little bit more favorable in that space. But we're also looking at continued collaboration with Walter Reed, so not just through UCSB, but direct collaboration with Zaretza, and that would be on wound infections, and then the more typical AMR, global threat infections that I talked about are still on that list, just maybe a little bit lower.
Thanks. Any other questions from anyone? Well, we really appreciate your talk. Thank you so much.
Thank you all.
And we'll see people next month.
Thank you.
Bye.
Thanks.